Okay, so welcome all to live session 5. I will start the session. In the meantime, we'll see if anybody can join or not. Anyhow, so in this session, what we will go through, we'll go through different forces which will affect the metal transfer. So mostly we will work on different kinds of metal transfer, different forces which affect those metal transfer. What are their characteristics? Uh, the physics behind those generation of those forces, those things will cover up. And as the way I go through, I will initially cover up the theoretical portions of what professor has gone through in your earlier week in the video lectures, and then we'll try to solve few problems which will help you to understand those assignment problems, right? So let us start. So what are there those in terms of forces which affect the metal transfer? So there are mainly two types of forces, right? So in terms of forces, we have two types of forces. What are those two types of forces? One will help or aid transfer force, and another is the retarding one. No? So one will help you to drop the drop the melt pool over your weld material, which will help you to transfer those deposition, and one will retard those forces. So another is retarding transfer force. Correct. Now there are different forces which involved in this, like there are surface tension, you have viscosity, you have gravity, you can have those Lorentz force because of uh, electromagnetic uh, electromagnetic force. Then you have gravity. Then you also can have force due to impact of those electron and ion particles, right? So we will go one by one. Now, what is there in surface tension force? So we talk about surface tension force, right? So surface tension force is a kind of a retarding force, uh, which will try to keep your droplet in its same position, right? It will not help you to deposit onto your weld metal. It will restrict your drop metal in its own position, you know. And what is the equation through which you can measure the surface tension force? So if Fs is my surface tension force, we can measure it through equation like this. So here D is your electrode dia. Now it may happen that your electrode dia and droplet dia is not similar, right? So over here you have your electrode dia, D is electrode dia, sigma is your surface tension, sigma is my surface tension, maybe in Newton per mm, force per length, whatever you follow, the unit, and K is called capillary constant. This is capillary constant. It normally varies from something around 0.6 to 1, right? Now, as I was saying, it may happen that your electrode and droplet dia will always not be similar, and during that time, your equation will be something like this. So, this will be my equation through which I can measure the surface tension force on your uh, electrode dia and droplet dia is different, right? So Re is my electrode dia and R is my droplet dia which I am depositing over your weld mixture. So through this you can measure the surface tension force over there. Then you have those viscosity, right? So you have also viscosity. Now, is it a retaining force or is it a aiding force? So viscosity also a retarding force. It is kind of whenever your high velocity gas jet will strike the job and it will always get back uh, or it will retard the movement of the metal drop, right? So let's say this is your electrode and this is your workpiece and it will form the arc and because of those formation of gas jets over here it will strike the workpiece and it will return back or apply those forces over your arc position to keep it in its uh, in its same position, right? So there can be this high velocity gas jet. Then you can have, so let me rub this up. So you can have high velocity gas jet. Then you can have force due to metal vapor. Right? What is there in force due to metal vapor? So you are generating some molten metal over there, right? So because you are generating molten metal, there will be vapor generation, and it will be evaporated from bottom of the drop, and the whirlpool will move in your upward direction, right? So due to that upward movement of the metal vapor, it acts against the molten metal drop hanging at the tip of the electrode. So if this is your drop metal and this is your electrode, so that force due to metal vapor which is generating due to that uh, generation of vapor or evaporation which is taking place, that will retard your movement of this droplet, and it will try it will try to make this droplet in such a way that it hangs in at the tip of the electrode, right? Then of course you have that gravity taking place. So whenever you are doing some uh, joining, when you are keeping electrode in the downward direction, gravity will help you, right? It is a detaching force when you are welding in some kind of flat position. But in case of overhead welding, if you are joining some overhead joining, when you have to move in the upward direction, gravity force will act as a retarding force, right? So gravity force will act as a retarding force while doing overhead welding, right? And what is the force of gravity? It depends on your volume of the droplet, right? If you are having electrode and let's say this is my droplet dia, it will have some diameter. So it will depend on your volume. So if this is spherical in nature, what will be the volume? 4/3 pi r cube, correct? And the force of gravity will be what? mg, no? So if g is acting downwards and the mass of the system will be rho into 4 third pi r cube into g. So this is my force due to gravity. Now, what are other forces you can think of? So, we have talked about this viscosity, we have talked about this gravity force. Um, then you have this force due to impact which takes place, right? So, always we talked about this uh, charging carriers, right? So, in the arc, there will be formation of electrons and ions, and they make some electron bridging, and because of that, the arc is getting generated, right? So you'll have electrons. So let me, if this is your arc over here, you will have electrons. You will have positive ions also. So if my electrode is connecting in the negative terminal and my workpiece is positive terminal, so my ions will be moving to the electrode. This we have talked a lot, and electrons will move to the workpiece side, the positive side, right? So as the polarity, as the polarity charged particles, those ions and electrons, they move towards those electrode and workpiece, they eventually come up with those impacting with one another, right? That's why their kinetic energy gets generated, and it ends up with loss of it. So it rise your temperature, right? Now, how can we find out the force due to impact? It's simply, so force due to impact will be m dvdt, the momentum, right? What is m? M is my mass of the charged particle. M is my mass of the charged particle, and dvdt is the velocity gradient over time. The acceleration, you can talk it, you can tell it acceleration, right? So we talked about this force due to this impact of those charged carrier. Then you can have Lorentz force, right? So Lorentz force generally generates due to this interaction of this arc current, and this is a self-induced force for this magnetic field generation, right? And you always will experience some kind of pinch effect. So we call it pinch effect when you will have some uh, neck forming generation. So if this is my, so let's say this is my arm and this is the workpiece, it will form some kind of necking over there. So let me draw it in a good way. So this is my arm, and these are those asymmetric radial force due to this electromagnetic self-induced magnetic field, and always this force experience some pinch effect where you'll have those neck formation, right? Now this neck formation will help you in terms of detachment of the drop. So with time progresses, it will make you detachment of the drop, this pinch effect, you know. right? Now, this self-induced magnetic field, what I was talking about, it generates due to this result of interaction of this arc current with its magnetic field, those Lorentz force which is getting generated. Uh, that results in something called plasma streaming. So Lorentz force will generate something called plasma streaming, right? Now, yeah. So surface tension and viscosity, which we till now discussed, uh, that help the droplet to grow in size, whereas this electromagnetic force or this Lorentz force that will constrict this molten end of the electrode due to this drop separation from the electrode, right? And then we have talked about this polarity of this direct current, straight direct current, uh, reverse polarity a lot of times. So we have talked about this straight and reverse polarity, right? What is there in straight polarity? What is there in straight polarity? In straight polarity, we say electrode is negative, right? So this electrode, this is straight polarity, and this is reverse polarity, right? So in reverse polarity, so when you are connecting your workpiece to negative and electrode to your positive end, so uh, 75% of the heat, I have talked about this, two-third of the heat or 75% of the heat that gets generated at the electrode over here. 75% heat at electrode, and this is vice versa. So the rest of the heat gets generated at the electrode over here. See over here, 25% heat at electrode. What are the other differences of electrode positive and electrode negative? The electrode positive, wherever you are using those consumable electrodes, like in submerged arc or shielded metal arc, uh, during during those processes, you have to use DCEP, or the reverse polarity is preferable because during that time less penetration happens, heat effective zone is less, and the oxide cleaning that takes place, that is good over there. Now, whenever you are using non-consumable electrode, whenever you are using non-consumable electrode, uh, during that time your heat effective zone will be wider in nature, and sufficient fusion and penetration will happen in this straight polarity thing, right? Yeah. So we talked about those forces affecting those metal transfer. Now, basically, metal. What is metal transfer? Whenever you are electric arc is struck between that job and your electrode, that the arcing end, because of you are doing some short circuiting and you are increasing your current density a lot at that end, that arcing end of the electrode that starts melting, and it takes kind of spherical shape and it hangs towards the job. So, and then because of those forces, either it will detach from that electrode, or it will retard, or it will keep it in its same position, right? Now, yeah. So those size of the droplet, so characterizing that metal transfer, uh, which we will go through. So different kinds of metal transfer. Uh, that metal transfer, the rate of the metal transfer that affects the weld bit geometry, microstructure, strength of the joint, those things. And how can you study the metal transfer? By simply setting up some high speed camera and then checking that how it is looking like in terms of how is the transfer going on, in terms of what is the droplet dia, what is the rate of the transfer, and yeah, the bead width, those things you can do some image processing analysis in terms of analyzing the metal transfer characteristics. Now, in terms of classification of metal transfer, in terms of classification of metal transfer, sorry, what are different metal transfer we have learned. So we have free flight transfer. In free flight transfer, what are there? You have globular metal transfer, then you can have spray metal transfer, and explosive one. These are my three different kinds of free flight metal transfer. Then you can have contact kind of transfer, where we have this bridging, then you can have short circuiting. Those are my different kinds of metal transfer. And lastly, you have a slag protected transfer. So these are my three kinds of metal transfer, which generally we classify the metal transfer in these three ways, right? Okay, let me rub this out initially. So we have already talked about these forces affecting this metal transfer, right? So you remember that, let's say if you have this electrode, sorry, if you have this electrode, if this is my electrode, let's say this is my arc, and over here, this is the workpiece. So let's say this is my current direction. So what are the forces we talked about? We talked about surface tension, we talked about gravity, we talked about uh, those Lorentz force, you know, due to electromagnetic interaction, right? So I told that your force of gravity can be it may be retaining or some kind of detaching force, right? Depending on whether your electrode is positioning upward or downward. Now, surface tension always will tend to retain the liquid drop at the tip of the electrode, right? This force depends on the radius of the electrode always. Those capillary constant, those density of the liquid metal. These are the parameters which will affect your surface tension force. Now, that electromagnetic force, which I was which I was indicating it as Lorentz force, uh, that is set up due to interaction of the electric current with its own magnetic field, right? So, electric current plus own magnetic field will give you Lorentz force, correct? Now, yeah, yeah. So we are at that classification of metal transfer. Now, when we will call it a globular metal transfer, when we will call it a spray metal transfer, when we will call it a jet metal transfer, those are uh, everything are free flight transfer, right? So those are the classifications of my free flight transfer where metal drops get detached from the electrode and it pass through the arc and deposit on the workpiece, right? So depending on geometry of your depending on geometry of your droplet dia, you will characterize those free flight transfer. So if so, let's say DD is my droplet dia, and DE is my electrode dia. So I have four classifications. If DD is three times of DE, we call it subthreshold. If DD is 2DE, we call it globular. If DD is DE, we call it spray transfer. And if DD is half of electrode there, call it jet metal transfer. So that is the most fine droplet you can think of, right? Sorry. So we are talking about globular metal transfer. What is there in globular metal transfer? So your, as I was saying, your droplet dia will be approximately twice of your electrode dia, and it is observed mostly in your low arc current. So if we talk about this globular one, it happens with low arc current and higher voltage. Higher voltage means your arc length will be higher, right? And those globules will pass freely through the welding arc, and depending on your size and gap of the arc, it may possible that it will short circuit the arc, right? And in globular transfer, because the droplet dia is big enough, that transfer will cause some kind of scatter loss, and penetration depth will be very shallow over there. So these are the characteristics of your globular metal transfer. So you will have uh, scatter loss, and then you can have penetration height is smaller over there, right? So after globular transfer, what is there? Um, we are having that spray transfer, right? Now, in spray, your either it is equal or yeah, it's almost that droplet dye is almost equal to that core electrode core wire dia, and the rate of drop is much higher over here, because your size of the droplet is uh, less than the globules. Whenever it is forming, the rate of droplet transfer, the deposition rate over your workpiece will be higher in your spray metal transfer, right? And those will be continuous phase, and that occurs at high current and lower current. So that is just opposite to your globular transfer. So if we talk about spray metal transfer, deposition rate is higher, occurs with high arc current and lower plane, right? So mostly spray mode type of transfer produces your stable kind of arc, and the penetration depth will be very deep over there, mostly recommended for thicker plates, and it will form some kind of the weld bead what it will form will be uh, aesthetically very good, right? Now in spray transfer, you are having three different categories. In spray transfer also, I can have different categories of spray. So one is this projected kind of metal transfer. Then you can have streaming metal transfer. Then you can have rotating metal transfer. It depends on how much current value you are passing through your arc current, right? So in your project, so for most of the cases, electromagnetic force is my main governing force. So for this projected streaming and rotating spray metal transfer, for each of those cases, my main governing force is electromagnetic force. Correct? Now, how can you characterize those projected spray metal transfer? You will have small droplets, uh, maybe close to electrode dia or somewhat less than electrode dia. So your droplet size will be very small, which will transfer from your electrode tip to the whirlpool. Then the spatter loss will be very less over here. So it will be kind of regular kind of droplet deposition over your workpiece, and can only be used in flat position, right? Because of uh, large volume of the molten pool it is generating. Mostly this projected spray metal transfer happens in flat position. So if we see the droplet size with current value, there will be some transition current, after which there will be some transition current, after which this will uh, this will form into your projected spray kind of thing, and before which it will be globular one. So if we try to draw the figure of this droplet size to current, so initially it will be all globular, then you will have this transition current over there, after which it will form to a projected spray metal transfer, right? Now, in terms of streaming spray metal transfer, again, as I said, electromagnetic force is your main governing force. However, uh, there will be further increase in your welding current. So whenever you increase your welding current more than what you are doing for whenever you are doing for this projected spray, you will end up with this streaming spray one. So what is happening over here? There will be, as you are increasing the current a lot over here, there will be more heat produced at the electrode tip, right? So let me drop this on. If this is my electrode, it will get tapered like this, and because of some less area, so there will be concentric heat generation, or local heat generation at that region. I will call it local heat generation. I know. So as a result, that that electrode where which was which was heated a lot, it becomes plastic, and that result in that tapered shape of that electrode end, right? And because of that, those fine droplets are formed and get detached from that electrode end. So you'll have those fine droplets over your workpiece. So this is my streaming metal transfer, streaming spray metal transfer. Mm. And if you are increasing current more and more, you will end up with this rotating one. So there is this, rotating spray metal transfer. Now, further increasing the current level, right? More and more you are increasing current, you will finally ending up with this rotating spray one. Now, here your the electrode tapering effect what was happening during your this what was that? This that streaming spray, that is more pronounced over here, right? There will be more overheating, and yeah, that heat formation will be more and more over here, and strong electromagnetic force caused by this caused by this excessively high current that will result in your some rotation of your column away from your straight line flow, right? So if your electrode is like this, and let's say my tapering is taking place like this, so there will be some rotation of your column and it will end up with some very fine droplets with a high amount of current level. So this is my workpiece. Here the droplets are extremely fine that are detached from the tip of uh, that rotational arc, right? And generally, when you should go for this rotating spray metal transfer, that improve your sidewall penetration in your flat position. So it will improve my sidewall position, sidewall penetration. Sorry, it will improve my sidewall penetration and yeah, it will prevent that sagging of the molten pool. Correct. So this is on this spray metal transfer. You have this projected spray, then you have this rotating spray. Those are there, and then you have some other kind of metal transfer which is called explosive metal transfer. So in explosive metal transfer, it is like the droplets uh, which will be forming. Uh, those are attached to the electrode tip, uh, and and it ejects the material in an explosive manner in which those small droplets are small droplets are kind of spattered away or expelled from that molten part, right? Uh, Here the droplet spattered on the tip of the electrode after detachment. So if we try to characterize it, droplet spattered on the tip of electrode even after detachment. So that is why it is called the explosive one. And also some kind of chemical reaction takes place which between that gas metal inside the droplet and yeah, that is accompanied by I talked that considerable amount of fine spatter will be there. So the main governing forces of for this explosive one is my electromagnetic and chemical reaction. So these are my two governing forces which will result in that explosion uh, of those droplets, right? So these are all I'm talking about free flight metal transfer, right? So how will we characterize those free flight metal transfers? Or what is happening in terms of what is happening in terms of voltage drop or current characteristics over there, है ना? So that we should understand. Now, in that regard, even if you have gone through that video lecture, um, I will just briefly try to explain what is happening in terms of free flight metal transfer. So there will have different steps, right? You'll have different steps where your arc gap will goes on decreasing, and because because you are reducing your arc gap, there will be continuous decrease in your voltage drop up to certain time, and after that your drop will detach from the due to pinch effect you are forming the neck, and at that point of time your drop will get detached from that neck, and it will transfer to the jaw, right? And immediately what happens, that original gap is destroyed, and your arc voltage that jumps to your normal value, right? And then your next cycle starts. So just give me a moment, please. Yeah, sorry for the inconvenience. So we are having this electrode. This is my arc. This is my workpiece, right? So because of formation of your kind of droplets and pinch effect and neck formation, you are reducing the arc length. So my arc length is getting reduced. So this is my arc length now. So L2, this is L1. Sorry, just a moment. Yeah. So हाँ नवीन, मेरा क्लास चल रहा है यार, अभी मैं पिक नहीं कर पाऊंगा। हाँ चाबी मेरे पास है, मैं शिवा को बोला था बोलने के लिए। मैं अभी सबमिट करूंगा वो खत्म होने के बाद, मेरा टीए खत्म होने के बाद। 7:30 7:45 हो जाएगा। शिवा नहीं बोला क्या तुमको कुछ? ठीक है। नहीं नहीं ठीक है, मेरे पास ही है, गलती से वो मेरे पॉकेट में आ गया। हाँ हाँ हाँ। हाँ हाँ मैं दे दूंगा। हम्म। Yeah, sorry. So uh, my my arc length is getting changed and due to neck formation, uh, and because of that the voltage is getting decreased, and at certain moment of time you'll have some droplet formation like this. So my whatever whatever droplet it was forming in terms of spherical shape, it gets detached from that end. So now it will be depositing over the workpiece, and during that time what will happen? So in terms of voltage, in terms of voltage characteristics, what we can say that my voltage is getting decreased due to change in that arc length, and then this is the point when my droplet is getting detached from that electrode, right? So this is my first point, and this is the point where droplets get detached, and then it will restore that amount of voltage. So basically, whatever you are starting from, right? That is my original R gap, which is restored, and also the voltage is kind of jumping towards the normal value, right? And your next cycle starts. That's how it happened in terms of free flight metal transfer. Why don't we go through few of the questions, right? Uh, okay, before that we should cover the rest of the things, and then instantly we can finish the question and answer. Okay, first let me finish the theoretical part. So we talked about this free flight metal transfer. Then there was this contact type transfer, right? So in contact type transfer, you had this bridging metal transfer. You have bridging metal transfer. So whenever your electrode wire is subjected to some kind of low short circuit current, uh, you are contacting the drop pool. So surface tension becomes the driving force during that time. So surface tension is driving force in contact type metal transfer, right? And it reduces the importance of your pinch effect. So in any kind of contact type transfer, electromagnetic force doesn't come into picture, pinch effect or neck formation doesn't come into picture. Uh, whatever comes into picture is your surface tension force, right? So yeah. Now in bridging kind of thing, the scatter generation is not there, droplet repulsion is not there. So the bead appearance will be very smooth over here. So over here you'll have good uniform well bead appearance, right? And mostly this preferable for joining thin sheet metals. So thin sheet metal joining is preferable. right? Then you have then you have something called short circuit transfer. Now, in short circuit transfer, what happens is the liquid drop at the tip of the electrode that gets in contact with the whirlpool before being detached from the electrode, right? So at some point of time, at some point of time, your liquid drop will, um, yeah, your liquid drop that gets in contact with the whirlpool uh, before you see that detaching of that liquid drop from the electrode, and that's how the arc is momentarily short circuited, right? So however, what happens that due to surface tension uh, and your electromagnetic force, uh, those two forces will result in some kind of uh, the drop is pulled into the whirlpool, and the contact with the electrode gets broken. So what is happening, uh, whenever the hanging drop touches the base metal, so let's say this is my electrode and this is the droplet, and whenever it touches the base metal, the circuit is shorted, right? And whenever there is short circuit, my arc will get extinguishes. So this pinch effect increases due to increase of current during shorting. Like I told that whenever you are having this short circuit, there will be intense amount of current density, right? So due to increase in this current, there will be this pinch effect also increases, neck formation quickens, and ultimately the drop gets detached from the electrode, right? And the moment the drop is detached from the electrode, the circuit again open and are gets reignited, right? So yeah, that's how this short circuiting occurs. I'm not going into uh, I'm not going into that very specific specifications of what should be the electrode dia, what should be the uh, welding speed, those aspects. Let us stick to the physics aspect in terms of mechanism of how is it happening. If you try to understand in terms of characteristics of this short circuiting metal transfer, so I was telling that this neck formation will be quick enough because of uh, because of increased current density, and then at certain point of time that short circuit occurs and extinguishes that arc, and the voltage drops down. So if we try to figure out in terms of different steps, so let's say this is my electrode, this is my arc in workpiece, this is first case, then this is touching the workpiece, this is second case, then this is forming the neck, this is third case, and due to this pinch effect increases, uh, that neck formation quickens, and ultimately at point E, drop gets detached from the electrode. So let's say that this is get detached from the electrode. You know? So what will happen in terms of voltage drop? So from A to B, there will be certain voltage drop. Then whenever this neck formation is there will be sudden voltage drop. And from whenever there will be detachment, there will be increase in voltage and it gets restored to its original voltage position because the next cycle will get started, right? And how my current will look like? My current will look like something like this initially because this is the voltage is getting reduced. It will get reduced, then again increased, then again decreased, then again increased. So that's how it will go on with cycle to cycle. Mm. Then we have this slag protected transfer. So mostly slag protected transfer is have you use this or this kind of metal transfer happens if there is this slag formation or flux protection in your shielded metal arc or submerged arc welding. So that is there. And then you have some other kind of uh, metal transfer is also there, like you can have repelled type of metal transfer. You can have pulsed metal transfer. You can have some metal transfer from this filler wire, right? Now, what is there in repelled kind of thing? So, hmm. So if the resulting force directs in such a way that it directs your deposition, your drop metal away from the whirlpool, then the repelled transfer occurs, right? So this situation is can be encountered when some kind of CO2 is used as the shielding gas, and particularly at low and moderate currents. If you're using this kind of gas shielding over there, it basically uh, directs your drop away from the whirlpool, and yeah, so the gravitational transfer is not very reliable, and repelled transfer is undesirable since it causes too much of a spatter loss. So repel transfer causes too much of a spatter loss, right? So uh, let's say this is my electrode, and this is generating this arc. So excessive vapor, if it is forming due to those shielding gases, uh, the droplet appears to be repelled towards the side of the electrode. So it will move like this. It will move like this, and then finally it will move like uh, something like this. So this is your droplet which is getting repelled towards the side of the electrode, and yeah, that is due to this high velocity gas jet which is striking over your workpiece, and that is causing your droplets to get away from your whirlpool and is trying to uh, repelling it towards the side of that electrode. And when does it occurs? When your gravity and aerodynamic force exceeds the repelling earth forces, right? So droplet transfer occurs when your gravity force or the aerodynamic force, so I'm calling it F aerodynamic, that is greater than my F repelling. That is when the detachment will take place, right now. Okay, give me a moment. Hmm. So there is this explosive one, then is this repelled one, and then let us talk about something on this pulse transfer. I'm basically trying to cover up the things very quickly. Whatever have been covered in the complete week. So yeah. So pulse transfer, you can think it of some kind of controlled method of spray transfer where that occurs at some kind of constant current. And yeah, so in this case the transfer of the metal from that electrode tip that occurs only at a period of pulse, right? Or if there is any peak current. So as you know, in pulse transfer you will have that peak current and some amount of background current, right? You can control the deposition rate in terms of these pulses, and during the interval between those pulses you have to have that low background current that will help you to maintain the arc to keep the wire tip molten, but there will be no metal transfer, right? So it is so if this is my time and if this is current, you will have some pulses like this. So this is my background current. So let's say A point is my background current and B point is peak current, right? So this what happens in pulsed current transfer. Now during this transfer, initially it will form some kind of droplet. It will try to form this droplet. So let's say this is my workpiece, and then it will form that neck. So initially this is my one, then this is my two. So I am increasing my current, and then more neck will form. I'm increasing current more, and then when I detach, my current gets down, my current gets down, and during this there will be this background current to keep the molten to keep the metal in its molten state, but there will be no deposition, and then again I will increase the current and form this globular shape, right? So it happens in that way. And finally, this is the final content of this lecture. So you finally can have this additional filler wear, right? So this additional filler wear takes place. You can use this plasma arc or gas tungsten arc or oxyfuel gas. So these kind of welding techniques mostly use those filler wears, and that is melted by the application of heat without forming a part of the electric circuit. So this is kind of completely an external source of deposition, what you trying to fill up into the gap, right? So no electromagnetic force will be responsible for this metal deposition. Now the force acting on this droplet are similar uh, to those happen in gas metal or shielded metal. However, this pinch effect does not play any part, because this is an external part, right? That pinch effect, electromagnetic force, those are being absent, and most often this greasing mode or short circuiting mode of metal transfer is adopted to make the maximum use of the heat and heat in additional silverware kind of thing, right? But the there is there is some disadvantages, right? So the deposition efficiency is very low over here, uh, because you will have some the detachment of the droplet will be very delayed over here. So if you are using this metal transfer from filler wire, so it's mostly globular kind of transfer, you will have lower deposition efficiency and delayed detachment from the filler wire, right? So let us quickly go through the question. Just give me a moment. Uh, I'll go through the questions quickly. Whatever we have covered will not take much time. So, okay. So it says X-ray method is used to study spray metal transfer, globular metal transfer, slag metal transfer, and metal transfer with filler wire. So which one is true over here? So mostly X-ray method is used for slag metal transfer because the metal transfer which will take place, that will be a slag or flux protected, right? You cannot see in naked eye the metal transfer which will take place. So that's why the reason this X-ray method is used in slag metal transfer. Then in second question I ask, pinch effect is caused due to which force? Uh, which of course you know, it is due to the electromagnetic force, the self-induced the self-induced magnetic field with the interaction of the arc current. We are generating that electromagnetic force, and which is the reason you are forming that neck formation during the deposition, right? So that is what the pinch effect is. Then in my third question, I say that surface tension acting on a 5 mm dia of droplet with 10 mm dia of electrode is 10 Newton per mm. Uh, so I have missed the that capillarity constant over here. Let us take capillarity constant as 1. Why don't we take capillarity constant as 1? So uh, let me rub this on. Capillarity constant. We'll take this as 1. Hmm. So what is happening? So here my electrode and droplet is different, right? So I know that surface tension force is something like 2 sigma pi r e square by 4r, that into my capillary constant, right? Sigma is my surface tension force, which is given as 10 Newton per mm. So I will 2 into 10 into pi into what is electrode dia? Electrode dia is 10 mm. So 10 square by 4 into R. What is droplet dia? Droplet dia is 5 mm. So 4 into 5, that into 1. Right? So 4, 5 to 10. So I will end up with something around 100 pi Newton. So my surface tension force will come as 100 into pi Newton, right? Then I ask in streaming spray metal transfer occurs at a current which is higher than the rotating spray, at a current which is less than the projected spray, at a very low current which is just higher than the SCC metal transfer, and the current which is less than the rotating spray metal transfer current. Which one is true over here? So, as I said, that streaming spray is kind of the metal transfer. Uh, of course, there will be this transition current after which this spray metal transfer occurs and before which this globular kind of thing occurs. And it happens at a current which is less than the rotating spray. The rotating spray metal transfer is the finest droplet you can think it of. And you have to use some maximum amount of current to make it a rotating one, right? So streaming spray metal transfer, the current is less than the rotating one. Good to go. So then I say that keeping other parameters as constant, uh, if our current is double, the Lorentz force will be what? It will be increased by 4 times, decreased by 4 times. So what is there in Lorentz force? If you are increasing the current, your Lorentz force will get increased. This is directly proportional, but this is directly proportional to the square of the amperage, right? So your Lorentz force is mu I square by 8 pi. You know, what is mu? Mu is your magnetic permeability. I is current. Mu is my magnetic permeability. So this is directly proportional to the square of the amperage. So we say that keeping other parameters constant, so I keep magnetic permeability as constant. I'm just changing the current. What will be my effect on Lorentz force? So if my current, arc current is getting doubled, Lorentz force will increase by 4 times. So it will be 2 square, right? So 5a is true. Then my next question asks, if the droplet dia is double of the electrode dia and occurs below the transition current of the metal transfer, I just talked about that initially there will be globular and then you have this short circuit, sorry, the spray kind of transfer at this transition current. So this is my size of the droplet, this is my current, right? So what should be the correct answer? 6C is true, right? Then I ask, electromagnetic force doesn't play any role in projected metal transfer, rotating metal transfer, streaming metal transfer. For each of these transfer, these are my classifications of spray metal transfer. So you have to have this electromagnetic force which comes into picture. But if you are using this feeler wire, as I was mentioning in the last, there electromagnetic force will not take place, right? So 7D is true. Then I say current level is highest and droplet is finest in which kind of metal transfer? This is B. 8B is true. Rotating spray is the one. Then I say in explosive metal transfer, the main governing force is what? Is it electromagnetic? Is it surface tension? Or the electromagnetic and chemical reaction? Which one is true? So over here, electromagnetic and chemical reaction is the main governing force which will uh, govern the explosive metal transfer, right? And in my final question, I answer repelled metal transfer occurs when repelling force is less than the gravity and aerodynamic. When the gravity or aerodynamic will be more than this repelling one, the droplet will get detached, right? So this is what really uh, I hope in the next week more students will join. This will encourage me more. Okay, so you just go through the videos, the questions. If you have uh, if you have any kind of confusion, you can ask professor. You can mail me. I'll try to get to that. Okay. So okay, this is what for now. Thank you.